All right, today's lesson is about hydrocarbons, more specifically alkenes. Now, if you guys remember my video introducing organic chemistry, you'll remember that alkenes have the general formula CnH2n. So just keep that in mind as we're solving this, or as we're going through this worksheet, or explanation, I guess. So, alkenes, or more specifically compounds in general, are going to have isomers. If you don't know what an isomer is, it's essentially a group of compounds that have the same molecular formula but different structural formulas. So we take three types of isomers: positional, structural, and geometrical. As a reminder, in alkenes, two of the carbons are double bonded to each other. So this is going to be there in that alkene no matter what. So in alkenes, the first type of isomer is positional, meaning the position of the double bond is different. C, double bond C. This is H3, this is H, H3. H2, H, H2, H3. If we look at these, both of these are C4, H8, C4, H8. However, the position of the double bond, let me pull out another color. The position of the double bond is different. Here, it's in the second bond location. Here, it's in the first bond location. So that is what a positional isomer is. Now, structural isomers are isomers that are branched differently. For example, oh wait, no. Actually, no, I'll just make that a 2. Okay, and then CH3, CH, double bond C, double bond, or single bond CH2, bond CH3. So here you can see the location of the double bond is the same, which means it's not a positional isomer. However, here there's 1, 2, 3, 4, 5. It's a long chain. Here there's 1, 2, 3, 4 with a fifth one hanging down. That's a structural isomer. The look of this is different than the look of this. There's a different number of branches, or the branches are in different locations. Finally, we have geometrical isomers. For geometrical isomers, the alkene that you're looking at has to have the structure R, CH, double bond, CH, R. R can be anything. It can be another hydrogen. It can be, what else can it be? It can be CH3, it can be C2H5, it can be anything, right? It needs to have this structure. What geometrical isomers are, let's take, for example, C4H8, okay? Let's just draw that out really quick. We're gonna say that the double bond is at the second location. You've got 1, 2, 3, 4. 1, 2, 3, 3. Okay, so this is just the linear form of C4H8, right? The geometrical isomers of that, what we need to do is, let me grab a pencil 1 second. That should work. We take this, okay? We draw that in the middle. Well, not in the middle. C double bonded to C, okay? And there's a hydrogen coming out of it, right? And then you draw whatever else is connected to this, which in this case is CH3, CH3. Now, you can notice that as I drew this, I drew the hydrogens on the same side. They're both on the bottom. This makes it the cis geometrical form. So in this case, it's, cis 2-butene, okay? The other isomer for the geometrical isomers would be to take this hydrogen right here and switch it with this. This stays in its place, So what we have is carbon double bonded to carbon, a hydrogen coming down out of this side, and a hydrogen going up out of this side. And then the CH3 and the CH3 are like this. Here, the hydrogens are opposite to each other, which makes it trans 2-butene. That is the difference between geometrical isomers. Now, moving on to the more alkene, I guess, related part of the lesson. The reactions. The first reaction is the combustion reaction. This reaction says that, let me write this out for you. So the combustion reaction says that CnH2n plus 3n over 2 O2 gives NCO2 plus NH2O. Let's give a quick example for that. Let's say we've got the compound C6H12. Let's try and figure out how to fill in the rest of this. If you want, take a second and try and solve it yourself. What is the combustion reaction of this alkene? All right, excuse me. So we notice that N in this case is 6. So plugging this in, 3N, 3 times 6 is 18, divided by 2 is 9. So 9O2 gives NCO2, N in this case is 6. So 6CO2 plus NH2O, which in this case is, again, 6, so 6H2O. So that's your example of a combustion reaction. An alkene plus oxygen is going to give you carbon dioxide and water. The next reaction is called hydrogenation. I've got it written out right here. Hydrogenation. What this reaction is essentially adding hydrogen to an alkene to turn it into an alkane. So in hydrogenation, you have alkene plus hydrogen gas in the presence of platinum gives alkane. All right? So for example, if you have, okay, so let me just write out the general formula for you. CnH2n plus H2 in the presence of platinum gives CnH2n plus 2. Let me actually draw this out for you. That should make it easier to understand. So let's take, for example, C3H6 plus H2 gives platinum, in the presence of platinum gives C3H8. So for now, we're just gonna assume that this is one propene, okay? Just to make it easy on ourselves. Oh, by the way, when you're naming an alkene, remember that before the name of the alkene, you want to put the location of the double bond, which is either 1, 2, 3, 4, etc. Okay? So to draw this out for you, this is H2, H1, so H3 plus H2 gives. So what we can look at here is essentially this double bond right here, it becomes a single bond. And on either side of that bond, you add a hydrogen. So it becomes, let me use my black pen, CH2 plus 1, because it's one hydrogen, bonded to CH1 plus 1, bonded to CH3, which doesn't change because it's not touched by the double bond. So we can then turn that into CH3, CH2, CH3, which if we count that up, gives this formula right here. Moving on, halogenation. Halogenation is the addition of a halogen. Remember, halogens are Cl2, Br2, I2, and Fe2. Okay? So Cl, in this case, Cl, Br, I, and Fe are X. Okay, we're gonna name them as X. So, halogenation, you can read it right here, halogenation is, we're gonna take it like this, let me show you. It's essentially C double bonded to C. Remember, R is anything, it doesn't matter what it is. Okay, so you've got just a normal alkene here, plus X2. So one of these options, it's either Cl2, Bl2, I2, or Fe2. Gives carbon bonded singularly to carbon, attached to H, R, and then X. So again, what happened here is that whatever this is came to the double bond right here and removed the double bond, making it a single bond, and instead attached an X in its place. Does that make sense? If not, try and rewatch it, and if you still didn't understand it, leave a comment or something and I will try and re-explain. Next. Oh wait, actually let me give you a real life example just to make it more clear. Let's say we have C2H5, C double bond C, CH3, hydrogen, plus Br2. If you want to take a second to try and solve it, feel free to do that now. Okay, good job. We have C bonded singularly to carbon, remember, this double bond becomes a single bond. And what's up here doesn't change, it just stays the same. C2H5, CH3, because again, the Br has nothing to do with any of this. It only touches and works with the double bond. Okay, obviously a hydrogen, and then Br here, Br here. Excuse me. Next, hydrohalogenation. If you look at this word, hydrohalogenation, notice something. Let me just write it out in like all caps or something. Hydrohalogenation. Ignore my messy writing. Hydrogenation, if you remember, is the addition of H2. Halogenation is the addition of X2, right? So what hydrohalogenation is alkene added to it HX. So again, X is either Cl, Br, I, or Fe. So hydrohalogenation is alkene plus HX, which gives, so Cn H2n plus 1X. All right? Now, there's a special case for this. It's called Markovnikov's rule. And remember this for the rest of our reactions because they will come in handy. If you have, okay, I'm gonna give you two options. CH bonded to CH and C bonded to CH. Okay, if you have these two, let's start with CH bonded to CH, okay? And to it, you wanna add Cl, whoa, pencil just broke. You wanna add Cl and hydrogen. Is it gonna matter where you put each one? No, because if you add Cl here and hydrogen here, it's gonna stay the same. If you, okay, and remember the double bond is gonna be broken. If you add hydrogen here and Cl here, it doesn't make a difference because it's just essentially that in reverse. However, if you wanna add Cl here and hydrogen here, it does make a difference because you can either get CCl bonded to CH2 or CH bonded to CHCl. And that is a difference. So what this difference is called major and minor. What you want to do, you want to look at the double bond, the location of the double bond. If on both sides of it, they're equal, number of hydrogens, let's say it's 2 hydrogens on this side, 2 hydrogens on this side, or 1 hydrogen on this side, 1 hydrogen on this side, or even no hydrogens on this side and no hydrogens on this side, then there is no major and minor. You just complete it normally. However, if on both sides of the double bond, there's a different number of hydrogens, for example, 1, 2, 0, 2, 1, 3, doesn't matter, right? As long as there's a different number on either side of the double bond, we apply what's called Markovnikov's rule, okay? There are 2 cases for this. Let me see if I have any other colors. We use a highlighter, marker thing. Actually, I have a marker. Let's use that if it works. Okay, so there are 2 cases to this rule, right? As you can see right here, there's 2 options for it. There's what's called major and what's called minor. Okay, so the important thing to note, you can think of it like this. In the major product of it, or in the major answer of it, the hydrogen is gonna go to the carbon that has more hydrogens, okay? So remember we said it's H plus X, or HX that we're adding in. So there's a hydrogen that we're adding in. That hydrogen, if it goes to the carbon that has more hydrogens, then we call the reaction, or the product, I guess, major. However, so for example, in this case, right, going back to C double bonded to CH, what would be the major answer of this? We said major is when hydrogen goes to the more hydrogenated carbon, so the carbon that has more hydrogens, which means, in this case, the hydrogen would go here. It would become, let's say you're at, okay, I'll give an example later, okay? Minor, on the other hand, is when the hydrogen goes to the carbon that has less hydrogens. Okay, so it's the same thing as major, just in reverse. So I'm gonna give you guys an example. Let's say I'm gonna make this really simple. CH3, CH double bonded to CH2 plus HCl. What does that give? It gives 2 options. Start with the major one. The major one says, okay, first of all, locate the double bond. We're working with these 2 right here. Which side has more hydrogen? Is it CH or CH2? Obviously, it's CH2. So for the major, okay, for the major product of this reaction, the hydrogen is gonna go to the carbon that has more hydrogens, which is in this case, CH2. So double bond is broken. It's a single bond right now. We've got an H here and a couple of H's here. We've got 2 H's here. However, this is major, which means that the hydrogen goes to the carbon that has more hydrogens, as we said, which means it goes right here. This becomes CH3, which means whatever's left over, which in this case is Cl, will go here. Now for the minor version of this, it's in reverse. So which of these 2 has less hydrogens? In this case, it's CH. So again, double bond is broken, okay? In this case, the hydrogen goes to the carbon that has less hydrogens, so the less hydrogenated one, which makes it CH2. And whatever's left over from here, which in this case again is Cl, goes to the more hydrogenated one. So CH2, Cl. Pretty easy. Now, moving on to hydration. Hydration is how we get alcohol. And most of us are minors, so please be careful not to drink any of this because we're not allowed to drink alcohol, obviously. Now, that was a stupid joke. Okay. Hydration says that an alkene plus H2O, so you're adding water to an alkene, will get you alcohol. Right? Okay. Let's give an example. Okay, before we actually give an example, I want to remind you of something. H2O is not H2 and O. It is H plus and OH minus. Just remember that as we solve this because it's going to come in handy. So let's take our alkene. All right, sorry about that. My storage was full. I had to clear it. So where were we? Okay, so remember H2O gives H plus and OH minus, which you need to keep in mind as you're continuing with this. So I took this expression right here, right? CH3 plus H2O in the presence of an acid and heat will give C3H8O. For purposes of making this easier on everyone, including myself, I'm just going to take one propene, which is also the only possible variant of propene. Now, looking at this right here, do you guys notice something about it? The double bond on either side of it has different number of hydrogens. And because H plus and OH minus are different things, they're not the same, they're not the same thing, they're not both hydrogen. One's H plus, one's OH minus. It means that depending on where we put these, we're gonna have different answers. So again, we're gonna do major and minor. So the products are C8, let me make sure you guys can see, yeah. CH3, we added the hydrogen here, bonded to CHOH, bonded to CH3. Okay, that's the first one. This could also be written as CH2O, up to you. Do you think this is the major or the minor product? If you guys guessed major, you would be correct, because the hydrogen went to the more hydrogenated carbon. Now, the minor version of this, I'm assuming you can guess it. If you can't, sit for a minute and try and figure it out. Good job. The minor version of this is going to be CH2, OH, CH2, CH3, obviously. So this again could be CH3. What? That is not right. Oh wait, no, yes it is. CH3O to CH2 to CH3. So that is the minor right there. That is how you do hydration. Now, moving on to the final part of this, it's called ozonolysis. Ozonolysis. Ozonolysis is when you take an alkene, okay, you add ozone, which is O3, and what is produced is called a carbonyl. Okay? Carbonyl and ZNO. Now, if you're wondering where the ZN came from, remember, ozonolysis is done in the presence of zinc. So, I'm trying to figure out how I want to explain this. Let's start like this. Carbonyls have two types. You can have what's called an aldehyde or a ketone. Okay? An aldehyde, actually, let me explain the rest before I continue with this. So, alkene, let me give you, let's give CH3, CH, double bond CH, CH3, plus O3. If you guys want to try and take a guess at what's going to happen, honestly, you'd probably be wrong because I could not figure out what on earth would happen the first time I watched this. So if you know, good job. You guys are really smart. Take this double bond right here. Okay? This time, instead of breaking it, split it into two. So now what you have is CH3. Actually, I want to change this just a little bit. 1 second. Let me rewrite this just because I want to have a specific point at the end of this. So CH3, CH double bond, C, CH3, CH3. Okay, back to what I was saying. See this double bond? We don't want to break it in half. Sorry, we don't want to split it, or we don't want to break it and just make it a single bond. We want to split it in half. So what we have now is CH3, CH double bonded to something, and a double bond to C, we don't know what it's bonded to yet, which is bonded to CH3 and CH3. So now, don't we have a bunch of oxygens just lying around? We can stick an oxygen here and an oxygen here. So now we have, look at this. We've got this right here and this right here, right? So what's the difference between these? Do you guys notice a difference between these? This carbon right here is bonded to 2 carbons. This carbon right here is bonded to a hydrogen and a carbon, okay? So this group right here is called a ketone group. This group right here is called an aldehyde group. Obviously, the last product of this reaction is going to be ZNO, but that is pretty easy to remember. So, an aldehyde group, how do you name it? You name it like this, alkanal, okay? Ketone group, how do you name it? Alkanone, okay? So, look at this. How many carbons do we have here? We have 2 carbons, which means it's ethane, or ethane. We can start it like this. Ethane, but then as you can see, the O here is bonded essentially at an extremity, you can consider it, which means it's ethanal. It's an aldehyde group. Now this side, there's 1, 2, 3 carbons, okay, which would make it propan something. And you can see here that the O is not bonded to an extremity. It's bonded to something in the middle, which makes it propanone, okay? That's kind of all you need to know about ozonolysis. One important thing to note is that the general formula of a carbonyl, which is this thing up here, is CnH2nO. That's something important to note. One other important thing to note is that if you have the aldehyde, if you have the 2 carbonyls, okay, there's a way to find the alkene from it. Didn't we say that at this double bond, we split it into 2 bonds and we stuck an O at the end of each side? What if we were to just remove those O's and stick the double bonds back together? Wouldn't this and this be the same? It absolutely would. And that is how you go from 2 carbonyls to an alkene. Thank you for watching.